All right, strap in everyone, because today we're going deep on some really mind-bending stuff.
Oh, yeah.
Many-valued logic. You with me?
I am.
You know how we usually think of things as true or false? Like it's just one or the other?
Yeah, that's how we're taught. The classic binary.
Well, get ready to challenge that very idea.
Ooh, exciting.
Many-valued logic, MVL for short,
Catchy.
says, hey, what if there's a whole range of truth, not just those two poles?
So not just black and white, but like shades of gray.
Exactly. We're using the Stanford Encyclopedia of Philosophy's entry on MVL for this deep dive. And fair warning, it's dense. But don't worry, we're here to break it down.
Distill it down, make it fun.
So the big idea, right off the bat, MVL allows for degrees of truth. It's like a dimmer switch instead of just on or off.
I like that analogy. A dimmer switch for truth.
So how does this actually work?
Yeah.
What are these degrees of truth, and how do they all fit together in a system?
Right. Good question. These degrees of truth, sometimes they're called truth degrees, can be represented in different ways. Numbers, sets, other objects, all depends on the specific system we're talking about.
Right.
But often, you'll see 0 for totally false, 1 for absolutely true, and everything in between. Well, that's where those shades of gray come in.
I'm already starting to see how this could be useful, especially when we're dealing with concepts that aren't so easily defined.
Exactly. Like, think about tall or heavy.
Yeah.
In classical logic, you have to say someone is tall or is not tall.
Right, no in between.
But MVL lets us say, well, they're kind of tall or they're really tall.
Oh.
Much more nuanced, right?
Way more realistic to how we actually think and talk.
Exactly.
But then, how do we build a whole logical system around this idea of degrees of truth? How does that even work?
That's where this idea of a logical matrix comes in.
Okay, a logical matrix. Sounds kind of intimidating.
It's not that bad. It's basically the blueprint for an MVL system.
So like the foundation on which it's built.
Yeah, think of it that way. It defines 3 main things.
Okay, lay it on me.
First, it tells us what our truth degrees are. Are we using numbers, sets, or something else entirely? Defines the players in the game.
Gotcha. Wow.
Then second, it lays down the rules for how those logical connectives we're all familiar with, like and, or, and not.
Yeah, the basics.
How those work with these new truth degrees.
Ah, so the rules of the game can change depending on the system.
Oh, absolutely. And lastly, the logical matrix specifies which truth degrees are considered designated, meaning they're taking on the role of true in this particular system.
Interesting. So it's not just about having more truth values, it's about redefining what true even means within this new framework.
You got it.
Okay, all this is super interesting, but I need an example to really get it. Can you give me one of these MVL systems in action?
Of course. Let's look at Ukasiewicz logic. It's a classic.
All right, Ukasiewicz logic.
It uses all those numbers between 0 and 1 as its truth degrees.
Whoa, every single one. That's a lot of shades of gray.
Right, and what's really cool is how it defines those connectives we were talking about, like and, the conjunction.
Yeah.
It's calculated by taking the maximum of 0 and then the sum of the 2 truth degrees minus 1.
Hold on. That's way more complicated than just saying true and true equals true, like we do normally.
Right.
Can we walk through an example, see it in action?
Sure. Imagine we've got 2 statements. The sky is blue with a truth degree of, say, 0.8.
Okay, mostly true.
And then the grass is green, but with a truth degree of, say, 0.6.
A little less true.
Right. Now, in Ukasiewicz logic, to figure out the truth of the sky is blue and D, the grass is green, we'd use that formula I mentioned.
Okay, walk me through it.
So we add those truth degrees, 0.8 plus 0.6, we get 1.4.
Right.
Subtract 1, that's 0.4.
Okay.
And since that's greater than 0, the truth degree of the whole statement, the sky is blue and the grass is green, is 0.4.
So what does that 0.4 truth degree actually mean?
It's saying that the combination of both those statements being true is somewhat true, but not as true as either statement on its own.
So it's like the sky is mostly blue and the grass is kind of green. So yeah, that's sort of true overall.
Exactly. And remember, that's just conjunction. Negation, implication, those have their own unique definitions in Ukasiewicz logic, too.
So this one system already shows us a totally different way of thinking about truth and logic.
And this is just the beginning. There are so many more MVL systems out there, each with its own quirks and ways of representing the nuances of truth.
I'm ready for more. Ukasiewicz logic was pretty wild.
It's a good one, right?
Yeah.
But we're just getting started.
Are there other MVL systems that use that same kind of approach? like with the truth degrees between 0 and 1.
Oh, absolutely. There's a whole family of them, actually, called Gödel logics,
Gödel logics. Okay, that name sounds familiar, but
named after Kurt Gödel.
yeah, but remind me.
Oh, sure. Kurt Gödel, super famous mathematician and logician.
Right.
Made some huge contributions to the whole field, like the foundations of mathematics.
It's coming back to me now.
His incompleteness theorems
Yeah, those were mind-blowing.
totally changed how we think about formal systems.
They were about proving stuff,
Right.
even if the statements are actually
Yeah,
true.
exactly. Showed there were inherent limitations.
Wow. Okay, so back to Gödel logics.
Yeah, so Gödel himself, he didn't actually develop these logics,
Okay,
but they're named after him
I see.
because they kind of capture some of the ideas from his work on intuitionistic logic,
Okay,
which also, challenge those classical assumptions.
got it. So how are Gödel logics different from Łukasiewicz's logic? I mean, if they both use those truth degrees between 0 and 1,
The key difference is in how they define those connectives.
the and or that kind of thing.
Yeah, all those familiar ones, but the rules for how they work with the truth degrees, those are what set them apart.
So specifics, what about conjunction in Gödel logics? How does that work?
Conjunction. Oh, it's actually pretty straightforward. You just take the minimum of the two truth degrees.
So lowest one wins.
Yep, the truth of the whole thing is determined by the truth of its least true part, like the weakest link in a chain.
That makes sense. What about disjunction?
Disjunction, that's the opposite. It's the maximum of the two truth degrees.
So the strongest link sets the bar.
You got it. Now, implication, that gets a bit more interesting.
Oh, I love interesting. Tell me more.
So the truth degree of an implication is 1.
Okay, full truth.
If the truth degree of the antecedent, that's the if part, is less than or equal to the consequent, the then part.
Okay.
Otherwise, it takes on the truth degree of the consequent.
That's a little tricky example.
Sure. Imagine this implication. If it's raining, then the ground is wet.
Classic.
Right. So if it's raining has a truth degree of, say, 0.4,
Okay. Little rain?
and the ground is wet is 0.7,
More true.
then the whole implication would have a truth degree of 1. Totally true.
Because even a little rain makes the ground wet.
Right. Exactly. But if the antecedent's truth degree is higher than the consequence,
Like it's raining a lot, but the ground isn't that wet.
yeah, then the implication's truth degree is limited by that consequence. So in that case, only 0.4.
Okay, so the then part kind of holds it back.
Right. It's a bit counterintuitive, but it makes sense in Gödel logic.
What about negation? How's that work?
Negation's simple. If the truth degree of a statement is 0, then its negation is 1, full truth.
Okay.
Otherwise, it's 0.
So black and white with negation, huh? Even in a system with shades of gray.
You could say that. Either completely flips it or it's totally false.
So Łukasiewicz and Gödel, both using that unit interval, but different rules for how those connectives work.
And that's what gives them their own unique characteristic.
This is awesome. But I'm a visual person. Any way we can see these differences play out, like in a real example.
Absolutely. Let's take a look at that classic philosophical puzzle, the Sorite's paradox.
The heap of sand paradox. That one always messes with me.
Right, so 1 grain of sand isn't a heap.
Definitely not.
And if you add 1 grain to something that's not a heap, it's still not a heap, right?
Right, it's just one more grain.
So the paradox says no matter how many grains you add, you'll never have a heap.
Yeah, because where's the line? It all seems so arbitrary.
Exactly. Now, MVL systems like Łukasiewicz and Gödel can offer a way to model this kind of vague reasoning.
Oh, interesting. How so?
Let's say we have this statement, n grains of sand make a heap. We'll call it Pn.
All right, PM.
In classical logic, that's either true or false for any given number of grains.
Right, but in MVL.
We can give Pn truth degrees that show that gradual change from not a heap to heap.
So like a smooth transition instead of a sudden jump.
Exactly. Now, in Łukasiewicz logic, as we add more sand, so as n increases, the truth degree of Pn would smoothly decrease.
Okay.
From 1, totally true for a tiny amount of sand, towards 0, totally false for a huge amount.
It's like a sliding scale of heapness.
Yeah, you could think of it that way. What about in Gödel logics?
What happens there?
In Gödel, the truth degree stays at 1 for a while, completely true, and then suddenly drops to 0 at a certain point.
So like there's a tipping point where it goes from heap to not a heap.
Exactly. Much more abrupt than in Łukasiewicz.
So different ways of handling vagueness, different perspectives.
Exactly. It's all about those different perspectives.
This is really cool. Makes you think about how we deal with fuzzy concepts.
It does. And before we move on, I have to ask,
Yeah.
Are there other MVL systems besides these two? There's a whole universe out there.
I bet.
One really interesting group is called T-norm-based systems.
T-norm-based systems. What's a T-norm?
It sounds complicated, but it's not too bad.
Okay, good.
Basically, a T-norm is a function that combines truth degrees,
Okay.
like a fancy AND operation.
So instead of true and true equals true, it's like somewhat true and very true equals mostly true.
Exactly. And the cool part is you can choose different T-norms,
Oh.
depending on what kind of logic you want to build.
So it's like a custom AND function?
Yeah. Different T-norms, different logics, different applications.
Powerful stuff.
It is. And we'll dig deeper into T-norms next time. They have some surprising connections to real-world stuff.
Can't wait. This whole MVL thing is blowing my mind.
I know, right? It's a whole new way of thinking about truth.
All right, back for more MVL. Still processing Ukasiewicz and Gödel. That was a lot.
I know, right? A lot to unpack there, but it gets even more interesting.
You said it. And we left off talking about T-norm-based systems, which sounded pretty complicated.
They sound worse than they are, I promise.
Okay, good, because I need a refresher. What is a T-norm?
Think of it as a function.
Okay.
It takes two of those truth degrees
Right.
and combines them to create a new one.
So customized and function?
Exactly. Like instead of that rigid true and true equals true, we can get somewhat true and very true equals mostly true.
Ah, I see. So it gives us more flexibility.
Exactly. And the beauty is we can pick and choose different T-norms.
We can. Why would we do that?
Because different T-norms create different kinds of logics that are tailor-made for specific situations.
Oh, that's pretty cool. Can you give me an example? See a T-norm in action?
Sure. Remember Ukasiewicz logic?
Yeah, the one with the crazy formula.
That's the one. Turns out that's actually a T-norm-based system.
Really?
Yeah. That formula for conjunction, the maximum of 0 and the sum of the truth degrees minus 1,
Right.
that's a specific type of T-norm.
So when we were doing those calculations, like the sky is blue and the grass is green, having a truth degree of 0.4, we were using a T-norm without even knowing it.
Yep. And you know what else? Gödel logic. That's T-norm based too.
No way. What's its T-norm?
Simple, just the minimum function.
So always going with the weakest link.
You got it. Now let's branch out a bit. Have you heard of product logic?
Product logic. No, that's a new one.
Pretty straightforward. Its T-norm is just multiplication.
Like times tables multiplication.
Exactly. So if you have two propositions, one with truth degree 0.8, the other 0.6, their conjunction in product logic, 0.48.
Makes sense. So what's product logic good for?
It's good for modeling things like evidence building up or beliefs getting stronger over time.
So like the more evidence we gather, the more true a statement becomes.
Exactly. Different T-norms, different ways of combining truth, different applications. It's a whole toolbox.
Okay, starting to get the big picture now. But I gotta ask, why should we even care about MVL? How does this connect to real life?
The age-old question. Philosophers have been wrestling with that one for a while.
I bet they have. So what's the answer?
Well, I think it's about expanding how we understand truth and reasoning, going beyond those limitations of classical logic.
Okay, I like where this is going. Tell me more.
Classical logic, with its true or false, it just doesn't cut it for a lot of real-world stuff.
Yeah, like the world's not always so black and white.
Exactly. So many things are vague, uncertain. Trying to force them into that binary system just doesn't work.
Like that heap of sand paradox?
Exactly. MVL gives us a more nuanced way to deal with those fuzzy concepts, allows for degrees of truth.
It's a more accurate map of reality with all the gray areas.
I like that. And, this has implications for tons of fields.
Oh, I bet. Like
Well, in computer science, you have fuzzy logic.
fuzzy logic, I've heard of that.
It's based on MVL principles.
Really?
Yeah, used in everything from control systems to medical diagnosis.
Oh.
Helps your washing machine figure out how to wash your clothes, that kind of thing.
No way. I use fuzzy logic every day and didn't even know it.
Probably. But what about philosophy? That's your domain, right?
It is. So what does MVL mean for philosophy?
It makes us rethink what truth even means.
Okay, yeah, that's a big one.
Suggests that truth isn't always black and white, that there might be shades in between.
So no more absolute truth.
Not necessarily, but it does tell us to be more critical, more nuanced in how we think about it.
Truth is more complex than we thought. This has been amazing. Never thought I'd get so excited about logic. But this MVL stuff, it really changes how you see the world.
I know, right? And this is just the tip of the iceberg. There's so much more to explore.
Oh, you've given me a lot to think about, that's for sure.
My pleasure. And hey, remember, next time someone tells you something's absolutely true, Remember that there might be a whole spectrum of truth out there you haven't even considered yet.
Great advice. I'll keep that in mind. Thanks for joining me on this deep dive into many-valued logic. It's been a wild ride.
Anytime. Always happy to talk logic.